Assalamualaikum and hi everyone. I will show you how to estimate an unknown mean from a single population denoted by mu. Let's go. Before going into details of the topic, let us look at the objectives you are expected to achieve at the end of this session. First, you should be able to obtain the point estimate for the population mean mu, either by calculating the point estimate if you have a set of sample data, or to identify the value of the point estimate if you are given a set of sample information. Second, you should be able to construct a confidence interval for mu. And finally, you should be able to interpret the constructed confidence interval for the population mean mu. Let's look at the point estimate for mu. How do you obtain the point estimate for the population mu? The answer is, you can simply calculate the sample mean from a set of sample data that you have already collected randomly. Let us look at the following example. Suppose you have a record on the speeds of 10 randomly selected cars recorded at particular spot of north-south highway, which are recorded in kilometers per hour. The point estimate of the true or population mean speed of all cars at the spot of north-south highway is simply the sample mean x bar, which you can directly calculate using any scientific calculator. The value of the point estimate in this example is x bar equals to 111.8 kilometers per hour. Now, how do you construct a confidence interval for the unknown population mean mu? You may refer to the textbook pages 65 to 67. If you recall from Chapter 2, Sample Distributions for the Sample Mean, here we have x bar, which is assumed to be normally distributed with mean mu and variance sigma squared over n, written as this. The standardized normal random variable for x bar is z, given as x bar minus mu over sigma divided by square root of n. Notice that the distribution of x bar and standardized z are both given in the formula booklet, page 2. Now let us focus on mu here to be our parameter of interest. Leaving mu alone, we have the following expression. By borrowing this expression or formula, we can construct the confidence interval for mu. From Chapter 2, we know that mu can be expressed as x bar minus z times sigma divided by square root of n. By borrowing this expression, we then can construct the 100 times 1 minus alpha % confidence interval for mu, given by this expression. Notice that the capital X bar now changes to a small x bar, which is the point estimate for the population mu. The sign minus now changes to a plus minus sign, whereas the capital Z now changes to a small z value associated with alpha over 2. And finally, the sigma over square of n remains unchanged. You can also write the confidence interval for mu like this. Either using the inequalities where mu is in the middle without any bracket, or putting the open and closed brackets for the confidence interval directly without the notation mu in the middle. Note that you can use this approach if you have an information on the value of population standard deviation sigma or population variance sigma squared. We call this as case 1. There are 3 cases altogether for constructing the confidence interval for the population mean mu. Let us now look at all 3 cases. Case 1, when you know the value of population standard deviation sigma or the variance sigma squared for any sample size n, be it small or large, the confidence interval for the mu is given as follows, exactly what we already did in the previous slide. However, when we do not know the value of population standard deviation sigma or the population variance sigma squared, then we need to ask further whether the sample size is small or large. If n is at least 30, that is, the sample size is large, then we have case 2. The confidence interval for mu is then given as follows. Notice that we can still use z alpha over 2. However, the unknown sigma is now replaced or estimated by the sample standard deviation s. When we do not know the population standard deviation sigma or the variance sigma squared, and the sample size n is small, that is less than 30, then we have case 3. The confidence interval for mu is then given as follows. You may notice that we can no longer use z alpha over 2. Instead, we should use t alpha over 2 nu, which depends on the degrees of freedom mu given as n minus 1. Note that the values of z alpha can be obtained from table 4, page 34, and the values of t alpha nu can be referred to Table 5, page 35. How are you doing so far, guys? I really hope that you are able to grab the fundamental concept from the previous slides. Now let us look at the simple example number 1. Suppose you have a sample mean x bar equals to 250, the population standard deviation sigma equals to 4, the sample standard deviation S equals to 4.5, and the sample size N equals to 16. The question is, construct a 95% confidence interval for the population mean mu. Before you answer the question, why don't you ask these following simple questions? What do you know from the statement? Yes, you're right. The population standard deviation sigma is known, isn't it? When it is known, then this is immediately case 1, where you do not have to question further whether the sample size is large or small. Here, if you notice, constructing a 95% confidence interval implies that we have alpha equals to 5% or 0.05. Therefore, alpha over 2 is 0.025. Hence, the 95% confidence interval for the population mean mu is then x bar, the sample mean, plus minus z alpha over 2, which is z 0.025 multiplied by the known population standard deviation sigma over the square root of the sample size n. Z 0.025 is 1.96 from table 4, page 34. Substituting the values accordingly, the required 95% confidence interval for the population mean mu is 248.04 and 251.96. You may notice that the lower limit must always be smaller than the upper limit. Next, we have a simple example number 2, guys. Are you ready? Oh yes. Similar question as before, but this time we do not have any information about the population standard deviation sigma. The question is, construct a 95% confidence interval for the population mean. Again, before answering the question, you need to ask the following questions. What do you know from the statement? Sigma value is missing, right? That is, sigma is unknown. When sigma is unknown, then you need to investigate further whether the sample size n is large or small. In this example, n equals to 36, which is greater than 30. Thus, the sample size is considered large. When sigma is unknown and the sample size is large, then we can identify this as case 2. That is, we can still use z and replace the unknown sigma by S. Therefore, the 95% confidence interval for mu is simply the sample mean plus minus z0.025 times the sample standard deviation S divided by the square root of the sample size n. As we know, z0.025 is 1.96 from table 4. Why is it 0.025? As before, we know that alpha is 5%, so alpha over 2 is 0.025. Hence, you have to use z0.025, which is 1.96. Substituting the values accordingly, the 95% confidence interval for the unknown population mean mu is then 248.53 and 251.47. Before we look at the simple example number 3, let us explore briefly a student's t-distribution or simply t-distribution. The t-distribution is bell-shaped and symmetrical about 0. The shape of t-distribution resembles the shape of the standardized z normal random variable, which has mean 0 and variance 1. However, the tails of the t-distribution are heavier when compared to the tails of z-distribution. The t-distribution is characterized by a degree of freedom denoted by nu, where nu is n-1. Values of t at alpha and nu are available in Table 5 in page 35. As the sample size n gets very large, it means that the degrees of freedom nu will also get large, and eventually T alpha nu will approach Z alpha. Now you may open Table 5 in your statistical table booklet, page 35. You may check for alpha equals to 0.05 and nu equals to 10. What is the t-value 0.0510? Can you see that the value is 1.812? If you get it, you are great. Now let's try again. What about t 0.00120? Here you need to go to nu equals to 20 and move vertically to alpha equals to 0.001. Can you see that the value is 3.552? Well done. Finally, can you identify the value of t 0.025 infinity? What is the value stated in the table? Do you get 1.96? Great! This is exactly the value of Z 0.025, which you can check in Table 4, page 34. Are you already familiar with the distribution? If yes, we can proceed to this simple example number 3. If not, I would suggest you to look again at the previous slide. Now, assuming you are already familiar with the t-distribution, let us look at this simple example number 3. Similar to the simple example number 2, let the sample mean x bar be 250, the sample standard deviation S be 4.5, and the sample size N to be 16. The same question, construct a 95% confidence interval for the population mean mu. Again, before you answer the question, you need to ask the following questions first. What do you know from the statement? Yes, you got it. The population standard deviation sigma or the population variance sigma squared is unknown, isn't it? When it is unknown, the next question to ask is, what is the sample size? Is it large or small? Here you can see that the sample size N equals to 16, which is obviously less than 30, isn't it? We can consider this as a small sample size. When both sigma is unknown and N is small, then we have case 3. Therefore, we cannot use Z anymore, but instead we should use T in our formula. Therefore, the 95% confidence interval for mu is x bar plus minus T alpha over 2 nu times the sample standard deviation S divided by the square root of the sample size N. Here, T alpha over 2 nu is T 0.02515. As we know, 0.025 is obtained from alpha over 2, where alpha is 5%, whereas nu equals to 15 is from 16 minus 1. From table 5, page 35, you can obtain the T 0.02515 value, which is 2.131. Substituting the values accordingly, then the 95% confidence interval for mu is 247.6 and 252.4. You may notice that the lower limit is smaller than the upper limit. For more practical examples on constructing the confidence interval for the unknown population mean mu, such as example 3.1 in page 66 and example 3.2 in page 69, you may apply the following steps. First, from a question or problem, recognize the information provided in the question and list down the information using the correct notations. For example, you may identify the value of x bar, sigma if it's known, S the sample standard deviation, and N the sample size. Second, identify the parameter of interest that you want to estimate. Third, choose the appropriate case if relevant. For example, in constructing the confidence interval for the unknown population mean mu, you have 3 cases altogether. So you need to select which of these cases is more suitable to answer the question, i.e. to construct the confidence interval for mu. Finally, solve the question and find the final answer. Hope you will find time to look at these two examples and look at the solutions and try to solve the questions on your own. You may then compare your answers with the answers given in the solutions. Hope you will enjoy the learning process. Let us now explore at this practical example that we have used before in finding the point estimate for the population mean mu. Do you remember? Using the same sample data, now we want to construct a 90% confidence interval for the population mean speed or the mean speed of all cars passing the particular spot of north-south highway. Here we have two questions, A and B. Both questions look the same. However, if you look closely at question A, you would notice that the population standard deviation sigma is known, isn't it? Here, the value of sigma is 7.5 kilometers per hour. Whereas, we do not have any information on sigma in question B. Can you identify which of these three cases is most suitable for each of these questions? In question A, sigma is known. Therefore, we will use case 1 immediately to construct the confidence interval for mu. We do not have to worry about the sample size, whether it is large or small in this question A. On the other hand, in question B, sigma is unknown. Then we have to look further at the sample size. Here the sample size n is 10, which is considered as small. Therefore, we will use case 3 to construct the confidence interval for mu. A point to highlight is that you always have to observe first whether the population standard deviation or the population variance is known or not. If it is known, then proceed to case 1. If not, then only you can look at the sample size. If it's large, use case 2. If it's small, proceed with case 3. A common mistake students tend to do is that when they look at the sample size first, where they tend to straightaway use case 3 when n is small, without noticing that sigma value is available in the first place, which requires them to use case 1. So please be careful at this stage. Look at sigma value first. If it's available, use case 1 immediately. If sigma value is unavailable, then only you look at the sample size, and if it's large, use case 2. If it's small, use case 3. The solutions for question A and question B in this practical example is explained in the following slide. To answer both questions A and B, we can follow the suggested steps discussed in earlier slide. First, recognize the information given in the question. In this practical example, since you are given a set of sample data, you need to calculate the sample mean and sample standard deviation first using your scientific calculator. The skill of using the scientific calculator to find the mean and the standard deviation of a set of data has been exposed in Chapter 1. Hope you can recall the technique. In this practical example, the sample mean is 111.8 that we have already obtained before, whereas the sample standard deviation is 7.9554. We already knew that the sample size is 10. We may not use the value of S in solving question A. However, we may need to use the value of S in question B. Second step, identify the parameter of interest. We knew that we are interested in constructing the confidence interval for the population mean mu. In the third step, we need to choose the appropriate case if relevant. As we know, we have 3 cases for estimating or constructing the confidence interval for mu. As mentioned before, case 1 is suitable for answering question A because the population standard deviation sigma is known. You do not have to worry about the sample size, whether it is small or large. Whereas case 3 is appropriate to be used for solving question B because the population standard deviation sigma is unknown and the sample size is small. Finally, substituting the values required in the appropriate approach, we can solve the question. Now let's look at the solution for question A and question B in this slide. First, question A. We know that we use case 1 where Z alpha over 2 and sigma will be in the formula. We will use sigma value that is known and Z 0.05 where 0.05 is alpha over 2 where alpha is 10% because we have 90% confidence interval. Substituting the values of x bar, Z alpha over 2, sigma, and the value of n, we have the following answer. The solution for question B, now we need to use case 3 where we need to replace Z with T alpha over 2 nu where T alpha over 2 nu is T 0.059. As you know, nu equals to 9 is a result from 10 minus 1. We cannot use sigma because sigma is unknown in question B. So sigma can be estimated or replaced by S. Substituting the values accordingly, we have the following answer. Notice that the value of T alpha over 2 nu, which is T 0.059, is 1.833 from table 5, page 35. And the value of S is 7.9554 that we have already obtained from the calculator earlier. You may notice that when sigma is unknown, we replace sigma by S. At the same level of confidence, the interval in question B is wider as compared to the confidence interval constructed for A. What can we say about this? We are actually saying that with unknown population standard deviation, the uncertainty is greater. Thus, the interval of the confidence level is wider. Let us now look at task 3.1 in page 67. A random sample of 16 compact cars tested for fuel consumption gave a mean of 12.5 km per liter with a standard deviation of 0.83 km per liter. Assuming that the fuel consumption in kilometers per liter of all compact cars have a normal distribution, construct a 99% confidence interval for the population mean of fuel consumption for compact cars. You may identify the information provided in this question. If you look at the first sentence, we have a random sample of size 16. Therefore, 16 refers to the sample size n. The mean of 12.5 refers to the value of x bar, and a standard deviation of 0.83 refers to the value of s. The focus of this question is to construct 99% confidence interval, and the parameter of interest is the population mean mu. Now, applying the steps I shared with you earlier, recognize the information given in the question. So we notice that the sample size n equals to 16, the sample mean x bar equals to 12.5, and the standard deviation s equals to 0.83. Next, identify the parameter of interest. As we noticed earlier, the parameter of interest that we want to construct the confidence interval of is mu, the population mean. And we know that there are 3 cases altogether. Looking at the information provided, we do not know the population sigma, and the sample size is small. Hence, we know that this is case 3. Finally, we can solve the question by substituting all the information provided and find the appropriate value of T alpha over 2 nu. Therefore, the 99% confidence interval for mu is x bar plus minus t alpha over 2 nu times s over square root of n. Here, t alpha over 2 nu refers to t 0.00515. How do we get 0.005 and how do we get nu equals to 15? Here you can see that alpha is 0.01 because we have a 99% confidence interval. Thus, alpha over 2 is 0.005. Whereas nu, the degrees of freedom, is n minus 1, where n is 16. When you minus 1, you get nu equals to 15. Therefore, we will use t 0.00515 in this formula. We can substitute the values that you obtained from the earlier slide, which is in the question. So we have here 12.5 plus minus 2.947 times 0.83 over square root of 16. 2.947 is the value of t 0.00515 that you can obtain from table 5 in page 35. Finally, using simple calculation, we have the final answer. 99% confidence interval for mu is 11.89 and 13.11 kilometers per hour. What is the interpretation of this answer? We may say that we are 99% confident that the interval 11.89 and 13.11 may contain the true population mean mu. Alternatively, we may say that the probability that the interval 11.89 to 13.11 may contain the true parameter value mu with the probability of 0.99. How do you interpret a confidence interval? Let's look at this question. Suppose the 90% confidence interval for the true mean speed of all cars passing a particular spot of north-south highway is given as follows. The confidence interval is 107.19 to 116.41. The question, are you 90% confident that the true mean speed is 110 kilometers per hour? That's the first question. What about the second question? Are you 90% confident that the true mean speed is 120 kilometers per hour? How do you answer these two questions when you change the value from 110 kilometers per hour to 120 kilometers per hour? Will your answers be the same for both questions or are they different? We will look at how we are going to answer these two questions in the next slide. For the first question, Are you 90% confident that the true mean speed is 110 kilometers per hour? The answer is yes. How do you justify your answer? Notice that the 90% confidence interval does contain the value of 110 kilometers per hour. However, for the question B, are you 90% confident that the true mean speed is 120 kilometers per hour? If you observe again the confidence interval at 90% level, it is obviously not containing the value 120, isn't it? So the answer is no. Again, how to justify? Because the 90% confidence interval does not contain the value of 120 kilometers per hour. In this final slide, let us do a checklist on the objective that I already listed down in the beginning of this session. Are you now able to obtain or calculate the point estimate for an unknown population mean mu? Remember that the point estimate for mu is simply the sample mean x bar that you can identify for a given sample information, or you may calculate the value of the sample mean using your scientific calculator if you are given a set of sample data. What about the second objective? Are you now able to construct a confidence interval for an unknown population mean mu? Remember, we had three cases in constructing the confidence interval for mu. And finally, are you able to interpret the confidence interval for mu? I really hope that you are able to achieve all these three objectives related to estimating the unknown population mean mu from a single population. I like to suggest that you should redo all the examples that I shared in these slides, in addition to doing example and task questions in the textbook, in order to gain a better understanding on the topic. Thank you for viewing, listening, and learning the topic. All the best to you and see you again in other topics. Wassalamualaikum warahmatullah and have a good day.